Hello, in this video we're going to look at relational algebra, which is the theory behind SQL, section 3.4 of the text. This is from page 27 of the text. In chapter 1, the term query language was defined as a non-procedural language in which the user gets to specify the data they want, but doesn't determine the process of retrieving the data. So what does that mean? When you're coding in a procedural language, let's say I'm coding in Java, you're going to have to specify with if statements and with loops how to manipulate the data. With a query language, you just say, this is how I want the data to be, and the database engine will determine what kind of if statements and what kind of loops are needed. That is called the query engine within the database. Specifically, structured query language, or SQL, is the query language used by relational databases. It is a standard. There are different flavors from database to database. So generally, if you know Oracle SQL, you really know SQL Server SQL. It might be a little bit different. So there'll be a little bit of a learning curve, but you don't ever have to start all over on learning SQL. There are two main subsets of SQL. And that is DML, data manipulation language, and this is managing the data itself in the database. Your student record, for example, is a data in a database, and so how are we going to manage that? That's DML. And then there's DDL, data definition language, and each of these have subsets within them, but right now, we're thinking about data models, correct? When you create a data model, you're going to have what's known as an ER diagram, and you might generate like a general table schema. And so DDL is the SQL that's actually going to create those tables and those indexes and those primary keys and those relationships that you define in your data model. What we're talking about with relational algebra relates to the DML part of SQL. So here are the 8 operations. They all come with an operator. Now, this is mathematics. It's relational algebra. And just like mathematics might have the division sign or the plus sign for addition, we have symbols here for each of these operations. So we have the sigma symbol for select, the pi symbol for project, union. I'm sure you've done union in set theory when you were younger. There's the intersect, again, a very well-known operation with set theory. There's the cross product, which uses the multiplication x operator. There's the join, and there are multiple types of join. It uses the theta symbol. And there's the difference. So the difference in relational algebra also uses the minus symbol. And there's a divide operation, and that uses the division symbol that you already know. Let's define rel-var, because in algebra you have variables, and in relational algebra we have variables. But in algebra, the variable represents a number, a real number probably. In relational algebra, the rel-var represents a relation. And you already know what a relation is. It looks like a table. It follows certain rules. And a rel-var will have a heading, and those heading field names can be used when we create these expressions. And it has the body, which is the data. So this is an example of an actual relation. But when I'm doing the algebra, I'll just maybe use the term P. In regular algebra, X might mean 14. In relational algebra, P means this relation. So it's just a substitute while we're writing our expression. And here is an expression. And in this case, the term customer is the rel-var. Doesn't have to be the same name as the table. Maybe you might use just C to represent the rel-var. Another thing related to mathematics is relational operators have the property of closure. For example, you know this, we've studied this in mathematics when we were younger, but when I multiply an integer with an integer, that operation called multiplication results in another integer every time. I can never get integer times an integer and get a fractional or a decimal value. That's because the operation of multiplication is closed within the integer set. Within relational algebra, Any operation that I do will take a relation and maybe do something with another relation, but in the end, what results is a relation. That's all that means. The first operation we're going to look at is select, and this really is vital to your SQL DML. Imagine this is just a relation and these are rows. We don't see the data. So the select is going to pick and choose what rows you're going to grab. You don't want every row in the relation, just certain rows. And in relational algebra, we're going to use the sigma, and then we're going to do a predicate. Now, a predicate is usually a relational operation using, let's say, greater than, less than. It has to be something that ends up being true or false. And then in parentheses, and this is my rel var, are here. So it works on a single relation. So it's a unary operator. And it defines a relation that contains only those tuples or rows of R that satisfy your condition. So where the condition is true. Example, list all staff with a salary greater than 10,000. This is how you would write it in relational algebra. Sigma, salary greater than 10,000, and there's my rel var representing the staff relation. Here's some example from the textbook. Here is my original relation, call it product. And you can actually do a relational operation that selects all from product. Our second example, we're selecting the price only if it's less than $2. So we look through, we're going to only pull out these two rows because those are the only two that are less than $2. And I would write this as sigma for the selection operation. The predicate is price less than 2. And then our rel var is the table name product. Next, we're going to select only those rows with a P code equal to 311452. So it's just looking through, and obviously that's only this one record here. And we would write that as sigma. The predicate is P code is equal to 311452. And then product then is our relation that we're working the operation on. Next operation is projection. And as you see by this image, projection is going to select all rows, but only certain fields or columns. So the expression looks like a pi symbol, and then just the list of columns that you want returned, and then in parentheses, the relation name or the rel var. So it works again on a single relation that's called unary, and it defines a relation that contains the vertical subset of R. An example, produce a list of salaries for all staff, showing only the staff number, the first name, the last name, and the salary details. So we use the pi operator, and then in the subset, we write down our column names, and then followed by that with a parenthesis and the relation name. Now here's an example from the text. Again, we've got our product, and all I want to know are the prices. So we're going to project the price field. That expression will be pi, which is the operator for projection. Price is the one column I want to retrieve. Product is the rel var or the relation name. So here we're going to pull out the product description and the price. And to do that, we use pi for our operation of projection. Here are our two field names. Here is the rel var for product. And finally, now we'll do the same thing. I'm not going to write this out, but it's going to be just like this. You're going to just substitute P code and price here, and that's going to retrieve these two columns. The union operation is a binary operation, meaning that it requires two relations, and it's very similar to the union of a set. Here we have one relation R and one relation S, and the union is just the combination of both of these. Duplicate rows are eliminated. One hiccup with the union is that R and S, those relations, must be union compatible. R has 4 columns. The relation S must have 4 columns. And not only that, they have to be the same type of domains. So if the first column is a phone number in R, you want something similar with S. They don't have to be the exact same field names, but they have to be the same domains. Here's an example of a union. Suppose we have a branch relation and a property for rent relation, and each of those has a city field. So in this case, we're combining projection, which is pi here, with union. So we're going to take the city field. That's what this is doing. Take the city field from branch, do the union operation with the city field from property for rent. This is from the textbook. If supplier and vendor are union compatible, then you can just do it like this. However, like the example with the branch and the property for rent, if they're not exactly the same, you can use the projection operation, and this says supplier name and this says vendor name, but they're both going to be text fields. So now this acts like a relation with one text field, and you're performing the union operation with another relation. Here's an example from the text. We have one relation that has a P code, a P descript, and price fields. And this happens to be the same. By the way, the union does not require that the field names be the same. This is just a coincidence. Very not likely to happen. But this union with this, it's just going to join. If there happens to be a duplicate, then the duplicates are eliminated because, as you know, duplicate rows are not allowed in a relation. The intersect is going to take R and S and only have the common rows as a result. And it's very much like intersect and set theory. Like a union, R and S must be union compatible. As an example, we're going to just grab the city field from branch and property for rent. This expression says, is there a city and branch that has properties for rent? List all of those. Here's an example. This time, notice that the field names aren't the same, but the first field is a first name for student and a last name for student, and this is for employee. But this is going to check, are there students that are also employees? And there's no George, Jane, Peter. Oh, there is a Franklin Johnson here. So those intersect. There's no Martin. And the result then is that intersection, that row that is in both of them. Here's the Cartesian product or the product. And we use the x like multiplication as the operator. We have here P. This is a relation. We have here another relation, Q. And the Cartesian product will combine A with 1, A with 2, A with 3, B with 1, B with 2, B with 3, and that's the result of P cross Q. So if you have 2 rows in P and 3 rows in Q, the result of the product is 6 rows. It's just multiplying the number of rows in each. A Cartesian product produces a set of sequences in which every member of one set is paired with every other member of the other set. I usually never do a product. There are exceptions. I can think of a few times where I've done this. Here is an example from the textbook. We've got product with these fields. And we have another table, maybe it's called location, with these fields. And the cross product is going to take flashlight, put it in 23, 24, 25. You see, the resulting set probably doesn't make a lot of sense. So it's not done a lot, but when it is done, it can result in a large result set. Our next operation is called a join, and there is multiple types of joins. You can think of a join as just the primary key foreign key relationship that we've been talking about since week 1 of class. In this example, we have a relation T that has fields A and B, and this data. We have a relation U with fields B and C with this data. The common field is B. So to do what's called a natural join, we're going to look at the first row. Is there a matching row here? And there is. So we're going to write A1X. Then we'll match it here, and that does not match. Then we'll take the second row. Do we have a match? Yes, so we'll write A1Y. Then we'll look at the second row and there's not a match. Then we'll take the third row here and match. Nope. Third row here and match. Nope. So natural joins will result in when the foreign key and the primary key match. Oh, but look, there's other kinds of joins, and I'm only going to discuss the outer joins from here. Notice that this natural join and outer join, this is called a left outer join, are exactly the same, except we have this additional row. So with the left outer join, T is the left part of the expression. So any rows, even if they don't have a match, are going to copy over. And any fields in the right relation will just have a null value. So natural join is done with 3 steps. Let's take a look at this table. This is the table that we're going to do a natural join with. A customer table, an agent table. A customer has an agent as a foreign key, and here's the agent code in agent as the primary key. So step 1 actually does the Cartesian product. So it's going to take this row, and there's 4 rows over here, so it's going to create a new row in the product table in step 1. We have 4 Walkers. Notice we have 4 Adaires. Rakowski 4, Rodriguez will have 4. This is the Cartesian product. That's step 1. In step 2, it's taking the result of the Cartesian product, and then it's going to do a select. If you recall, in select, we have a predicate. The predicate is that the 2 agent code fields, one that comes from where it's the foreign key in customer, and one that comes from where it's the primary key in agent, must be equal. If not, we're not going to include it. So we don't select this, we don't select this. We select that one. So that does become one of the rows in the result. And we do it again. We will select that one. So wherever they're equal, that's the selection. But we won't select that. We won't select that. So as you can see, by the time you run through all the rows and see where there's an equality between these 2 fields, that's going to be in the resulting set. And then step 3 is, this is kind of redundant. These are the same values. So what we're going to do is strike this or join this just into an agent code field. And that's a project. Remember, a project decides what columns you want to include, and we'll include agent code, and we can strike the agent since it's not a duplicate name now. Agent 421 did not have a match at all after step 1. There's no match. So agent 421 did not get written here to the resulting table. Sometimes we're just going to call natural join a join. I will just call it a join or an inner join. And here is how you can write it. It uses this. This is the symbol for a join or a natural join. Let's look at left and right outer joins. Recall that one agent that doesn't have any related customers. What if you want to see all agents, whether they have a customer or not? To write the expression for a left outer join, it's the same symbol. We're going to tuck some extra dashes here to the left. This would be a left outer join. That just means any extra columns that don't have a match, I don't care, we're going to include them. Just because this is left and this is right. This is a right outer join. So that there's any extra columns that don't have a match over in R, that's okay, we're going to include them. So what makes it left and right is just the order. This is the original table we had earlier. And here's a left outer join. We're going to call customer the left table and agent the right table. So here's our left outer join. Customer's the left table. And notice now we're including 421, even though there's not a 421 over here. Since there's a 421 here, and this is a left outer join, we're going to include it. Since there's not a 421 in agent, we also keep any field that came from agent null. Here's the right outer join. Since agent's to the right, so we have an agent that doesn't have any matching customers? We do. There's no customer with 333. So we have the row from agent here, but notice since there's not a related record and these fields come from customer, they're going to be null. And there are times, plenty of times, when I needed to do an outer join. The difference operation is going to take R, and here's all the rows in R, and here's all the rows in S. Everything in R that's not in S at all. So that results in this group right here. And we just use the minus symbol. R and S must be union compatible. And here's an example. List all cities where there's a branch office but no properties for rent. So here is all cities with a branch office. And then we're going to pull all cities with property for rent. And if there's a city here that doesn't have a city in here, then that's going to return. That will be part of the results. Here's an example from the text. Now we're going to do not the intersection, but the difference. So we're going to take a look at all these records and what is in here that is not in here. Well, since Frank Johnson is in here, I'm not going to include that, but I'm going to include the other 4 because they're not in here. Again, union compatible. These are union compatible, even though they're different tables and different field names. There's still a first name and a last name. If the tables you have are not union compatible, you can pick out just what you need using the projection. This results in a relation. Okay, it's a relation with 1 column. And this is a relation with 1 column, and you're taking the difference of those 2 relations. Now they're union compatible. And our last operation's called divide, and we use the division symbol. Don't think I've really ever used it myself. We have a large table here. Just think about division. You take the big number and you divide it by the small number, resulting in another small number. So we have a big table, and we're going to divide it by a table that has a common field, B. And this is how the operation looks like, V divided by W. And the result will be A, the field that's not in W, if every value in A matches every value in W. So A has a 1, 2, which is what W has. So A is going to be written over. B has a 1, 2, which is what W has. So B is going to be written over, but C only has a 1. So C is not in the result set. Here's an example. Identify all clients who have viewed all properties with 3 rooms. No, now we're getting a little more difficult. So I don't know if you recall from algebra, you always do the inner parentheses and work out. So we're going to do this one. We're going to select all the rows in property for rent that has the true statement rooms equal 3. Then from that set of rows, then we're going to project and only grab the property number. Now here's the viewing. So we're going to take the viewing relation and grab the client number and the property number. Then what we're going to do is divide that relation by this relation. So that'll be all clients who have viewed all properties for rent with 3 rooms. Here's an example in the text. Here's our initial relation. It looks like a composite entity, and we're going to divide it by the set of products with these IDs, and more or less it's just going to return the customer code if customer that has purchased all 3 of these, and it is these 2 customers. Let's just check. 130 pod 1 2 3 4 5 6 and 2 3 4 5 6 7 5 6 7 8 9 0. And 12, 550 probably bought the same 3. So those were the reasons that those were returned. Now, I can see a use for this. That might be a little bit more difficult using other operations. I'd have to think about it for a while, but this is a good example of the divide operation.